All right, so for 2, we're reviewing matrix multiplication from Algebra 2. We'll have a little bit of extension on it, though. We'll be applying this to some application problems. Now, matrix multiplication is not as simple as matrix addition and subtraction from the previous section. When you add and subtract matrices, you just add the corresponding elements or subtract the corresponding elements. For matrix multiplication, that is not the case. There's some properties with the dimensions of the matrices that we need for the product to be defined, right? So recall, for your product to be defined, that's only possible if and only if the number of columns in the first matrix equals the number of rows in the second matrix. Okay? So let's say I have matrix A, it's a 3 by 4 matrix, 3 rows by 4 columns. Matrix B is 4 by 2, 4 rows by 2 columns. Notice those inner 2 numbers are equal. The columns from A are equal to the columns from B, so that means the product is defined, and it will have dimensions 3 by 2. Okay? So applying that down below, these 2 numbers are equal, and therefore their dimensions will be the outer 2 numbers of 2 and 8. Mn will be a 2 by 8 matrix. For P and Q, inner dimensions are equal, so the product will be a 3 by 4 matrix. X and Y, though, these inner 2 values are not equal, so we will say XY is undefined. Okay? All right, now example 1, we're just going to review, so what is the process to find the element of the product matrix? Okay, so here I have matrix K. It's a 3 by 2 matrix. Matrix L is a 2 by 3 matrix, and I would like the product KL. Well, first of all, is it defined? Yes, the columns of K are equal to the rows of L. That's going to mean the product will be a 3 by 3 matrix. The size, the dimensions of the product are important, right? Because it's going to tell you how many elements you're after, okay? All right, so let's say I want to go after the first row, first column element. That means in matrix K, I use the first row elements. Matrix L, I use the first column elements. And the rule is you're going to go left to right, and you're going to go top to bottom. So I'm going to take the leftmost number of 1. I'm going to multiply it by the topmost number of -3. And that's going to give me -3. I'm going to then add that with the product of -2 and -1. So notice we are not only multiplying in this process, we are adding as well. Okay? Now I'm going to start to write the simplified version here. Okay? Good. Start right now. Okay, now I'm going to move to the second column of matrix L. And I'll repeat the process, left to right, top to bottom. So 1 times 2 is 2, added with -2 times -2, or 4. That's going to give me 6. Okay. Are you going to write anything down? No? Okay, now I move to the third column of matrix L. 1 times 2 is 2, added with -2 times 0 or 0. That's going to give me a 2. Now notice the first row of matrix K has been exhausted. I've used it with all 3 columns of L, right? So now I'm ready to move down to the second row of K, and I'll go back to the first column of L. So I'm going to take 4 times -3, that's -12, added with 3 times -1 or -3. And that'll give me -15 for that second row, first column element. Okay, we'll shift over to the second column there of L. 4 times 2 is 8, plus 3 times -2 or -6. That's going to give me 2. And we're going to shift over to the third column. 4 times 2, 8. 3 times 0, 0. 8 plus 0 is 8. Row 2's been exhausted, so now we move to row 3. I'm going to shift back to column 1. 0 times -3 plus -1 times -1. It's going to give me a 1. Shift to the second column. 0 times 2 is 0. Added with -1 times -2 or 2. And finally shift to the third column. You'll end up with a 0 plus 0 or 0. So there is your final matrix. Questions there? All right, so now, example 2, we're asked to find the product LK. Same dimension, or same matrices though. So matrix K is a 3 by 2. Matrix L is a 2 by 3. If I'm finding LK, I've got to look at the columns of L, which are 3, and the rows of K, which are also 3. So the product will be defined, and it will be a 2 by 2. Another square matrix, but with different dimensions. Okay? So I'm going to use the rows of L and the columns of K. Work left to right, top to bottom. All right, so -3 will multiply 1 and give me -3. Added with 2 times 4, which is 8. Added with 2 times 0, which is 0. So that's going to give me a 5. Okay, shift to column 2 here. Again, left to right, top to bottom. -3 times -2 would be 6. Add that to 2 times 3, also 6. Add that to 2 times -1 or -2. All together, those add to 10. All right, now shift down to the second row. Let's go back to the first column. -1 times 1 is -1. Added with -2 times 4 or -8. Added with 0. It's going to give us -9. And lastly, shift over to the second column of K. -1 times -2 would be 2. Added with -2 times 3 would be -6. Added with another 0, you end up with a -4. All right, now clearly this result is different from the previous result for the product of K and L, right? They are not equivalent, so what that shows me is that the commutative property does not hold true for matrix multiplication. Remember, the commutative property held true for matrix addition, but it is not working for multiplication. Okay. All right, so now let's look at some applications of matrix multiplication. All right, here we're told machine 1 and machine 2 produce items. They're producing shirts, hats, and pants at the hourly rate given in matrix A. Okay, so that first matrix, matrix H, is telling you how many of each type is produced per hour on each machine. Matrix D gives you the number of hours that each machine is running for every day of the week. All right, so first question, what does the 3 mean in matrix H? The amount of shirts being made off of machine 1 per hour. That's key, per hour. Okay. We're going to say machine 1, do it green. Machine 1 produces 3 shirts per hour. Okay, what about 4 in that same matrix? Well, that's machine 2 produces 4 hats per hour. All right, and then what does the 12 mean in matrix D? Yeah, machine 2 runs 12 hours on Wednesdays. Okay, now which is defined? The product HD or DH? Well, let's look at dimensions. Okay, so H is a 3 by 2. D is a 2 by 5. So based on the dimensions, can I find HD or DH? HD. Columns of H are equivalent to the rows of D. Okay, so that means the product HD is defined, and it will have dimensions 3 by 5, right? Okay, so let's start going after those elements. Okay, so I'm just going to do a few, and then I'll kind of speed the process up here. Okay, so if I want first row, first column, I'm going to take 3 and 2 with 8 and 6. So 3 times 8, 24, added with 2 times 6, or 12. I'll simplify that here in a minute. Okay, then I can just go down the line to the next column, but still use the first row of H. 3 times 8 again, 24. Added with 2 times 10, or 20. And I can repeat it. So next I'm going to get 24 added with 24, then 21 added with 22, then 21 added with 18. Okay, once you move down to row 2 in H, with column 1 from D, you'll get 40 plus 24. Next, 40 plus 40. 40 plus 48. 35 plus 44. And 35 plus 36. And then moving down to row 3, 8 plus 12. 8 plus 20, 8 plus 24, 7 plus 22, 7 plus 18. And now let me simplify all that. 36, 44, 48, 43, 39. Second row, 64, 80, 88, 79, and 71. Third row, 20, 28, 32, 29, and 25. Okay, now we got to make sense of the rows and the columns here. So the rows, there's 3 of them. They came from the rows of matrix H, right? So those represented in matrix H, shirts, hats, and pants. So we're going to list those here. Okay, and then the columns, the 5 columns came from matrix D, which represented the days of the week. Monday, Tuesday, Wednesday, Thursday, and Friday. Okay, so the final question, state what the element 36 means. This element right there. 36 shirts made on Monday by both machines, yes. Very good. All right, final example is a test grade example. We got grades for students A, B, C, D, and E stored in the matrix there over 5 different tests. It says tests 1, 2, and 4 are 15% of the final grade. Tests 3 and 5 are worth 25% and 30% respectively. So we want to use matrix multiplication to find the final average for each student. Okay, so we're going to need to multiply this 5 by 5 matrix with a matrix for the percentage that each test is worth, right? So part of this is knowing what should the dimensions be of the matrix and where should I place it so that the product is defined. You got a couple options. Okay, so we could do a 1 by 5 matrix. Maybe I'll place it over here where I'd have 15%, 0.15 for test 1. Same thing for test 2.
Isn't that a 5 by 1?
Did I say 1 by 5?
Yes.
I'm sorry. Yes, this is a 5 by 1. Okay, next would be, it said test 3's 25%. Test 4 is back to 15%, and test 5, 30%. So that would be one option as a 5 by 1. Okay. Other option could be a 1 by 5. Okay, would have the same elements. Run out of room. Okay. So notice where I placed each. If I'm going to use the 5 by 1, I have to place it to the right of this 5 by 5 matrix for the product to be defined, right? To have those two values equal. If I'm going to use the 1 by 5, I had to place it to the left for these two dimensions to be equal and make the product defined, right? So both products will be defined, but which one will actually do what I want it to do and give me the final average for each individual student? Should I use the 1 by 5 or the 5 by 1?
1 by 5.
Yeah, so think, if I go left to right, and then with this, let's say I'm using the first column here, I go top to bottom, that means I'm solely multiplying student A's test scores by each of these percentages and adding them up, right? Versus if I try to do it in the other direction, I'd have to go this row with this column, and if I'm working left to right and top to bottom, now I'm mixing all the students together, right? And that's just going to give me a score related to test one, not to related to each individual student, okay? So that doesn't really make sense for what we're trying to do here. So we're going to rule that one out. We're going to do the 1 by 5 with the 5 by 1. All right, I calculated it ahead of time. So you end up, it'll be a 1 by 5. And you end up, first element's 80.85. Second, 91.7. Third, 76.15.
These are real test averages.
92.05, not quite. And 94.1. I wish some of your averages were this high.
I mean, 80.85 is pretty.
Yeah. So A, B, C, D, E. Those are the 5 students' final averages. So let's go student E. Okay.